When a 300-meter cargo ship hits the water, the sheer physics of the displacement are staggering. Tens of thousands of tons of steel slide down a slipway to instantly battle the pressure of the ocean. But before a single steel plate is cut or a single weld is struck, this massive structure must be built in its entirety somewhere else first, inside a computer. For most of history, getting a vessel from concept to the slipway required huge drafting halls. Armies of draftsmen spent months generating thousands of paper drawings by hand, a process that increased the risk of transcription errors and costly rework once steel was being assembled on the berth. Sketching the rough outline of a boat is straightforward. Engineering a dynamic floating structure demands absolute precision. Today, shipbuilders rely on a digital pipeline to perfect the math long before physical construction begins. The challenge in ship design is that a vessel operates in a fluid, unpredictable environment. Every physical and performance characteristic is linked. You cannot optimize one metric in isolation. This diagram shows the interconnected variables of ship design. If you increase cargo capacity, the ship gets heavier. That extra weight requires more power, which means installing a larger engine. A larger engine forces you to alter the hull shape, which immediately alters the ship's stability. Naval architects resolve this chaos using a framework called the design spiral. Instead of getting trapped in a loop of conflicting requirements, they work through each parameter in strict sequence, updating their initial guesses and going around the loop again. With each pass, the adjustments get smaller. Eventually, the numbers stop changing. The design converges. The architect has successfully found the most economically efficient solution that satisfies all safety and performance constraints simultaneously. Reaching this mathematical lock digitally is vital. Erasing a line on a screen costs nothing. Discovering an engineering flaw during physical construction forces yards to scrap raw steel, delaying delivery by months and draining millions of dollars. The final output is the ship product model, a comprehensive digital twin containing the exact geometry, material grade, and location of every plate, pipe, and cable. This database serves as the strict blueprint that triggers the physical pipeline. The physical build begins in the stockyard. This operates as a precision logistics system where the digital model tracks thousands of tons of raw steel, assigning specific plates to the exact ship blocks they will eventually form. Not all of that steel is identical. Ordinary mild steel, known as grades A and B, is sufficient for the general hull plating. In regions subjected to intense bending loads, like the upper decks of a container ship, builders mandate high-tensile steel to maintain structural strength while reducing total weight. Operating environment also dictates chemistry. Steel has a transition temperature where it stops bending and instead fractures like glass. For vessels navigating freezing waters in the North Atlantic or Arctic routes, the digital twin specifies resilient, notch-tough materials like grades D and E. When these plates first arrive from the mill, they are rarely ready for precision cutting. Uneven cooling leaves the metal warped, and the surfaces are coated in a hard, brittle oxide layer called mill scale. To correct this, the plates are fed through heavy, counter-rotating rollers called mangles to press them completely flat. Next, automated machines propel millions of tiny steel balls at the metal to blast away the mill scale and rust. Finally, the steel receives a micro-thin layer of primer to prevent oxidation during assembly. Before a single blade or torch touches the metal, the raw material is flattened, cleaned, and protected. It is chemically and geometrically prepared to meet the tolerances demanded by the digital twin. The prepped plates move to the cutting floor. Here, the ship product model feeds exact part geometry straight into numerical control machines, entirely bypassing human transcription. The tool is matched to the specific job. Heavy keel sections are burned through using oxy-fuel torches. For medium-thickness hull plating, shipyards deploy a 20,000-degree plasma arc, melting the steel at extreme speeds to produce a narrow, heat-efficient edge. Cutting flat shapes is entirely automated, but a ship's hull is highly hydrodynamic. Portions of the bow, stern, and bilge require plates to be curved in two directions simultaneously, a geometric state known as double curvature. Standard mechanical rollers cannot bend rigid steel in two axes at once. Shipbuilders rely on a specialized manual craft called heat line bending, using fire rather than mechanical presses to warp the metal. By moving a torch in precise patterns, the operator heats the top surface, causing the steel molecules to expand. Rapidly quenching the metal with water forces localized plastic compression. The hot zone shrinks, pulling the rigid plate into a mathematically perfect curve. Forming a ship's hull requires the absolute data precision of an automated CAD model, physically executed through a direct manipulation of the metal's internal stresses. People often picture a ship being built from the keel up, rib by rib, directly on the slipway. Modern shipyards actually assemble vessels in prefabricated modular subunits. Building sections upside down or flat on a workshop floor allows gravity to work with the welders. It enables high-speed automated downhand welding, which produces stronger and faster joints and trying to weld overhead on an upright ship. The scale of these units escalates quickly. Flat two-dimensional steel panels are reinforced with stiffeners, then welded into large three-dimensional blocks. Before these blocks leave the shop, they are pre-outfitted with complex modules like pipe banks, ventilation shafts, and machinery bases. Only when these blocks are substantially complete do they move to the building berth. Erection almost always begins in the aft machinery space, where the heaviest structural components and the main engines are located. The shipyard then stacks the remaining blocks outward from there. The building berth operates as a final assembly line, where thousands of pre-outfitted components, now sealed inside their respective blocks, are finally stitched together into a single hull. With the massive blocks finally assembled, the yard faces one final hurdle. A modern cargo ship contains miles of human and robotic welds. Before the vessel is subjected to the crushing dynamic pressure of the open ocean, the structural integrity of those joints must be proven. Inspectors utilize non-destructive testing to peer inside the solid steel. They deploy industrial radiography to hunt for hidden internal voids within the weld pools, and apply magnetic particle testing to expose microscopic surface cracks in high-stress zones. Combined with intense pressure testing of the internal bulkheads, these structural inspections confirm that the physical steel sitting on the berth matches the exact mathematical promises generated by the digital twin. That mathematical certainty is about to face the physical reality of the slipway. A ship launch is a visual spectacle, but mechanically it is a high-stakes physics equation playing out in real time. This graph illustrates the two critical forces at play over the distance of the slipway, a downward weight moment line and an upward buoyancy moment line. As the ship slides toward the water, the buoyancy moment must constantly exceed the weight moment. If the calculations are flawed and the weight curve crosses the buoyancy curve before the hull is fully supported by the water, the launch fails. The unsupported stress will literally crack the massive steel structure in half. But when the naval architect balances the cradle design, the friction coefficient, and the weight distribution perfectly, gravity releases tens of thousands of tons of steel into the sea. A modern merchant vessel represents the culmination of this coordination, a project where virtual data, high-strength alloys, and precise logistical choreography converge to turn 60,000 tons of steel into a seaworthy machine.